Okay, so today's lecture is about push down automata. Let's see the basic structure of push down automata. The push down automata is an automation technique in which we are having a finite state machine as one of the part, and the second part is a stack. So if we are adding up the finite state machine with the stack operations, we can construct a push down automata. So how we can build up the components of any push down automation. So there are three components: the input tape that keeps the input whatever the string we need to validate, we need to put that string over the input tape. We need to have a control unit which controls the movement of finite state machine, and we need to have a stack with infinite size. That infinite size does not mean that we are having an infinite space of keeping variables over there. It means that there is no specific size of any stack. We can create the stack as per our need. So stack is a very formal structure of keeping the data, and the stack contains two basic operations, that is push and pop. So whatever we need to perform, we need to perform on the top symbol of the stack, and placing something in the stack means pushing, and to remove something or to read something from the stack is known as pop. So here's the flow of push down automata. That we are having the input tape, we take the values from the input tape, process in the finite control unit, that is the finite state machine structure, which accepts or rejects the word. At the same time, we are dealing with the stack by pushing the variables and popping out those variables as per the reduction or the shifting of context free grammar production. The formal description of push down automata contains 7 tuples. And what are these tuples? The very first one is Q, which contains the finite number of states. It belongs to the finite state machine. Sigma, it is the set of input alphabets. It belongs to the finite state machine. Stack symbols, it belongs to the stack part. Transition function, it contains the transition which happens in the finite state machine. At the same time, it also gives the operational activity of stack. Q naught is the initial state which belongs to the set of states, and I is the stack top symbol, whereas F is the set of accepting states. Again, it should be the member of state set, that is Q. So how we can graphically describe the push down automata? In the push down automata, we are having states and transitions. States must be named with whatever the way we used to do. Normally we use Q1 or Q2 just to define the state structure, and these state names helps us in order to structure a transition table or the transition function. So whatever we are doing over the transition, normally in the finite state machine we simply keeps the input character over the transition, but here we are having two things. One is the input symbol, the other thing is the stack operation. So very first member is reflects the stack top, and it produces C, means that we are replacing the stack top with the next value. So if we are having if we just want to push something over the stack without removing anything from there, so we can say epsilon arrow, the value which we want to push on the stack. if we simply wants to pop from the stack, so we can say the value which is basically on the stack top produces epsilon. So that in this way we can pop the value from stack. Or here B produces C defines the replacing of the stack top with the new variable or the new terminal. There is another description way which we normally use to say that this is instantaneous description, that is ID of any PDA, which is basically represented by a triplet Q, W and S. So it helps us in order to define the transition function. So Q defines the state and W defines the unconsumed input, whereas S defines the stack. So in this situation, whenever we are performing any transition function, so the transition function needs to have the state value as well as the input which we need to process and the stack content, that is the stack top value. So if we want to establish the overall transition function scheme, so we need to know that what is a turnstile notation. So the turnstile notation is basically used for connecting pairs of our descriptions which are instantaneous descriptions, which we have studied over here, this ID. So if we are connecting the pairs of IDs, we need to connect these pairs with the help of turnstile notation, and it gives the it shows the movements of the automation. So the process of transition is denoted by turnstile symbol, that is this horizontal T. So just assume that if we are having a PDA with these 7 tuples, our transition can be mathematically represented by the following notation. The P is the initial state, whereas Q shall be the final which we are getting up. AW is basically the input sequence, and we are having T beta as the stack top. So from this transition structure, from this ID, if we are jumping towards the new ID, so we are having a new state that is replaced with, it means that from P we are moving towards Q. AW, here A has been utilized, so we are simply having W as unconsumed string. Then T beta is converted into alpha B. So what does it mean? That alpha has, the T has been replaced by alpha. So this is how we can link up different ID pairs. And here is the description that this implies that while taking a transition from P to Q, the input A is consumed and the stack top T is replaced with a new string, that is alpha. So if we want 0 or more moves of PDA, we can use cleans closure, that is static over the turnstile notation, if we want to attempt multiple IDs or multiple transitions into it. Acceptability of PDA, there are two ways of acceptability of any PDA. The very first is the final state acceptability. That means that if we consume the input string completely and we reached to the final state without emptying the stack, because the stack is irrelevant in this situation, so we can say that okay, the input string has been consumed and we are standing at the final state. That means the input is accepted by the machine. Whereas there is another way of providing the acceptance by cleaning up the stack. So if we consumes the input string, and by consuming the all input string members, at the same time we cleans up the stack, so we can say the given input string is accepted by the PDA. We don't need to worry about where exactly we are standing in the transition machine. So there are two ways of acceptance in PDA. So for an example, we are having a language of 0 to the power n and 1 to the power n, where n is greater than or equal to 0. So it accepts epsilon if n is equal to 0, or 0 1 or 00 11 and 000 111. So if this is the case, so we can build up a PDA like this, that Q1 is the start state as well as the terminal state, because this machine accepts epsilon. In the first transition, we are reading nothing. We are reading no such input string and simply placing the dollar on the stack top. So it acts as the end marker or the stack special symbol, which defines the empty ness of stack. So we are simply placing the dollar in the beginning. Second, if we reach to the state Q2, and if the input string contains 0, so we are simply pushing the zeros over the stack. So epsilon produces 0, means we are simply filling up this stack with zeros, because what exactly happens in this language, that the total number of zeros must be equal to total number of ones. So we are, for example, if we are having 4 zeros, so all 4 zeros goes into the stack. And how we can count that how many ones can be accepted? So we can pop zeros while reading ones. So here is the transition, that we are reading 1 and we are popping out a 0. So if we have placed 4 zeros and we can read 4 ones, so all the 4 ones can remove all the 4 zeros from the stack. So it defines that total number of zeros and total number of ones are same. And in the end, if we finished up the input string, so it means that we don't need to read the input string, that is epsilon. At the same time, we are having dollar on the stack top, which gives us the signal that the stack is empty. So we can take out the dollar and reach to the final state, that is Q4. So this is how PDA works with any of the language which is context free language. So this is the example in which we are having 2 zeros and 2 ones. The step 1 in here, we are placing dollar on the top of the stack, so we can say that here is the dollar. Step 2, we are reading 0, the very first 0, and we are pushing 0 on the stack top. So 0 is over here again, so it is on the top of the dollar. Step 3, again we are reading 0, so it means that we need to have another 0 over the stack, so we just push 0 over the stack. Step 4, we are reading 1, so we jump from Q2 to Q3. So whenever we are reading 1, we are popping out 0. So 1 0 from the top has been removed by this particular transition, and the next one removes the second 0 from the stack. So the stack contains dollar on the top. The final situation defines the accepting state, where all the ones has been completed. It means that the input string is finished. So it ends with no transition or no input, means epsilon, and the stack top contains dollar. So we can take dollar out of the stack and reach to the final state, that is Q4. So again there is another example, which is a palindrome. Palindrome are those words which contains the same spelling, either we read it from the right hand side or from the left hand side. So that's why we call it W and WR. WR means reversed W, and it is the language of A's and B's. So if we are writing A, B, so the next component will be BA, so it becomes a palindrome ABBA. So this is the machine for making the palindrome, which is an even palindrome. And if you want to validate ABBA, so How we can do it? The very first step is same as the previous one. We are simply placing the dollar on the top. Step number 2, we read A, so we just push A on the top of the stack. We are reading B, so we push B on the top. The next B, we are taking the B out with the help of the next B, and then A with the help of A. So here we can see that from Q2 to Q3 we are taking out what we have pushed on the stack, and finally when the string is completed we can take the accepting state by removing the dollar from the stack top. So there is another transition in between which defines epsilon comma epsilon produces epsilon. So this is very much alike of the transition which we used to do in epsilon and FA. So we are transiting from Q2 to Q3 without reading anything from the input tape, as well as without doing anything over the stack. So this is the division of even palindrome. So this helps us to divide both the words, whether the word is in the normal fashion or in the reversed fashion. So how the machine knows that when we need to transit this particular transition, because it takes epsilon, so we can use this transition at any time. So what we need to do, we simply place epsilon in the beginning or after every character, just to identify that which position of epsilon is correct. So the very first epsilon, if we are taking this first epsilon, so with the help of the machine we can say, okay, we are reading epsilon, so epsilon is here, we are reading epsilon, and we are pushing the dollar on the stack, so this is fine. We jump down, we are reading A, so at Q2 we can read A and we can push this A over the stack. So here we can push the value of A over the stack, so this A is fine. After A there is an epsilon, so there are two possibilities, whether we accept this epsilon or we ignore this epsilon. If we accept the epsilon, we can move from Q2 to Q3, or if we rejects or ignores this epsilon, we can jump straight to the input entry, that is B. So that's why we are having a tree with two different branches. If we are accepting epsilon, so it means that epsilon produces epsilon, and it defines that okay, after epsilon there is B, and it means we are standing at Q3. So if we are reading B, the stack must contain B on the top, whereas previously we are having A on the top, so this transition cannot be ended successfully, so it's failed. So jumps back to the state where we can have another branch for validating the string. So here this epsilon is rejected with the help of machine, and we need to accept B. So whenever we are reading the B, we just simply push B on the top of the stack. So right now we are having B on the top, then A, and then dollar. Again after B we are having two different positions, whether we take this epsilon or we ignore this epsilon. If we accept the epsilon, it takes us to the right path which can accept the whole string. If we accept B, so we can jump to the we didn't jump, we simply takes the value at Q2 and we simply adds values over the stack. We will be unable to remove the values from the stack, and we stuck over there. So you can see that this X defines the invalid execution. So this particular path help us to reach to the final state. Therefore this the very first epsilon is fine according to the machine, the last epsilon is fine according to the machine, which help us to remove the dollar from the stack, and the center epsilon, which is basically a division of a symmetry, which defines the symmetry of the right hand side of the word and the left hand side of the word, whereas the other epsilons are ignorable. These epsilons are invalid. So that's all from my side. Thank you very much.